Thank you so much for joining us today. We have Dr. Ariane Ducellier today. It's our pleasure to host her at the Data Science Seminar. Ariane is a postdoctoral scholar at the Institute of Health Metrics and Evaluation at the University of Washington, working in the mathematical sciences and computational algorithms team. Dr. Ducellier completed her doctoral work in earth sciences at the University of Washington, where her research involved detecting and classifying earthquake events in large data sets of ground motion recordings. She also holds a master's degree in statistics from the University of Washington. Thank you so much, Ariane, and looking forward to your talk today. Thank you.
Okay. Thank you for inviting me, and I'm happy to present the works we're currently working on in the mathematical team at AHME. So I'm going to present today a work on raking methods and applications to health metrics. So I'm just going to briefly introduce the Institute for Health Metrics and Evaluation that is located in University of Washington. And the aim of the Institute is to produce data measurements about all data related to health and to global health, like the number of deaths, the causes of death, the number of people sick, and from which sickness they are sick, and what are the risks associated to different diseases. And the mathematical teams develop mathematical methods and algorithms for health metrics. So in particular, I'm working on raking methods. So I will talk first about a few motivating examples to explain what is raking. Then I will detail more the mathematical formulation of the raking problem. And then I will show you applications to some IHME datasets. So first, to start, a few motivating examples. So imagine that you have observations for a categorical variable x1. So that could be the different cause of death for people in a country. And you also have the margin, which could be the total number of deaths for any cause. And you suppose that the margin is known, that is, you know the total number of deaths for all causes. But for the observations, there are some uncertainties, so you're not totally sure about the observation. And if you sum the observation over all causes of death, you observe that you do not get to the sum, which is the total number of deaths. So there's probably some measurement error in your number of deaths for the different causes. So this is not really satisfying for HME to publish data like this, because we would like to have the number of deaths for each cause to add up correctly to the number of deaths for all possible causes. So we have to adjust the observations, so the sum of the observation add up correctly to the margins. So this is what you would have in a 1D problem. So similarly, you could imagine a 2D problem. So you would have two categorical variables, x1 and x2. So for instance, it could be the number of the cause of death for x1, and for x2, it could be the different regions in the country. And so you would have observation for each cause of death in each region, and you would need to make sure that they add up correctly to the margins. So here your margins could be for each region in the country, the total number of deaths, or for each cause of death, the total number of deaths for the entire country. And here you do not have necessarily observations that add up correctly, so you have to adjust them so that the observation add up correctly to the margins. You could also have, imagine a 3D problem. So in that case, you would have three categorical variables. And here in this example, I show margins where I have I sum the observation over one category, and also margins for the for all the possible combinations of the two different categories. here again, you would have to adjust the observations so that they match correctly the total numbers. So in all these different examples and also the talk, I'm supposing that here the margins are well known and they add up correctly. So if you were to sum all the margins over this direction and all the margins in over this direction, you would get the same number. And so we suppose that you do not have errors in the margins themselves and they add up correctly. So generally speaking, you can think of different number of cases, but the idea is always the same. You have some table of with observation for different categories, and you know the margins, and you want to adjust the observation to the margins. So the idea behind this work is that the uncertainty on the margin is usually smaller than the uncertainty on the observation. So for example, it is easier to get the total number of deaths than to get the number of deaths for each cause. So because you could have some measurement error with some deaths that are not attributed or they are attributed to two causes, so that would make measurements error. Or you can imagine that your observations are actually the output of the model, and the model may not be set up so that the number of deaths for each cause actually add up to the total number of deaths. So we want, so this is why we suppose that the margins are correct and we want to adjust the observations, because we could also think about the reverse problem, just taking the observation and then adding them up to get the margins. But in this way, we keep the small uncertainty on the margins and we adjust the observation where the risk of error is more likely. So in the general case, these observations are not going to add up to the margin. So this is why you have to make this adjustment in order to be able to publish data tables that are consistent and where users who will use this data table are going to find the same result no matter how they download their data and how much what manipulations they do to their data. If they add up numbers following one category or another category, they will always find the same numbers. And in all cases, we're going to adjust observation so that the values after adjustment match the known margin. So this process of adjustment is called raking. So I'm going now to look at more precisely to the mathematical formulation of this raking problem. So this classic raking problem is usually done for survey sampling. So this is a little bit different than the problem that we have at IHME, but the way we solve the problem is similar. So I'm just going to introduce what we do for survey sampling. So for survey sampling, you have a population, and you want to estimate the population total of some variable that takes values y for the population. So you want to estimate the sum. As it is survey sampling, you suppose that you're not going to know the value for the entire population, and you're going to take some sample from the population. And you have, for each individual of the population, the probability of having this individual taken in the sample. And so you can have an estimator of the total for the variable to which you have, about which you're looking for the total. So that would be the sum over the sample of the value that this variable takes for this individual divided by the probability of having this individual in your sample. So equivalently, you instead of working with 1 over the probability, we work with di, which is 1 over probability, and it is using the division. So that's why I'm working di here. So this is what you would do generally with surface sampling. And additionally, to make your sample a little better, you could think of having auxiliary variable for this individual. So for example, you could have data on individuals, for example, the regions where they live, the age, their ages, for example. And so this, for each individual, you would have this auxiliary variable. And you suppose that the value of the variable for each individual and each auxiliary variable is not necessarily known, but you suppose that the sum over all the population of this auxiliary variable is known. So, for example, for an entire population, you would know how many people live in each region, and you will know how many people belong to each age group. So instead of using the weights DI for the observation to estimate your variable, you're going to replace this weight DI by raking weights WI, so that the sum over the auxiliary variable is going to be equal to the known value of the auxiliary variable for the entire population. And then you have the raking estimator, which is the sum over the sample, by this time using your raking weights. So for our raking problem, which is a little bit different because we have an entire table and we know the values of the observation for each case in the table. This is just a particular case of this raking problem. So in that case, our sample would be the entire population. And so the probability of having the individual in the sample would be 1. And here we're going to work, instead of working with the raking weights, we're going to work directly with the raked values, which has the raking weights multiplied by the observations. Because ultimately, we are interested in how to replace the observations with an adjusted observation that I'm going to call the raking value. So in that case, our auxiliary variables would be the margins on the observation. So in 1D, the auxiliary variable would be the sum over all the categories. So this would be the auxiliary variable would be the value of the margin here. And in 2D, the auxiliary variable would be the values of the margins in the two categorical variables. So now we can finally write the raking problem as an optimization problem. So we're going to suppose that y are our initial observation in the table, beta as the unknown raked value. So this is what we want to know. And we have some constraints. So we're going to write the different sums over the different categorical variable under a matrix A that contain linear constraints. And the vector S will be our known margins. And we need to define a function f that is a sort of distance between the raked values and the observations. So this distance would be equal to 0 if the raked value is equal to the observation. And we want to minimize the distance between raked values and observation under the constraints that the linear constraints on the table are respected. So this distance is written as the sum of the distance for each case in the observation table. And we also add a raking weight. A raking weight, so we are able to give more weights to some observation and smaller weights to some observation, depending on how much certain we are of this observation. So different variations on the raking problem include different linear constraints. the choice of the Raking weights and also the choice of the distance function. The most important constraint for the distance function is that it has to be convex, so your optimization problem will be convex and it will be easy to solve. So now we can look at different distance functions that we can look at. So the first one is the chi-square function, which is like the least square between observation and rect value by but weighted by the value of the observation. And one advantage of this distance is that you can solve the optimization problem in one iteration. So this is a very fast solution. We have the anthropic distance, which is a bit more complicated and involves the logarithm of the ratio between the observation, the rect value and the observation. One advantage of this formula is that the solution of the problem will take this form. So the rect value will be equal to the observation multiplied by an exponential. So in particular, that means that your rect value is going to have the same sign as the initial observation. So this is particularly important for health metrics because, for example, if we are often interested in metrics that must stay positive, so the number of deaths will always be positive, and we want the rect value to also be positive, so that our table makes sense. And another distance function that we can use is the logit distance, which is more complicated. But one important thing about this logit distance is when you look at the solution of the problem, the rect value can stay between a lower bound and an upper bound, and they are guaranteed to stay between this lower bound and upper bound. And this is particularly important if you want to rec prevalence observation. So we want to know the percentage of people who have some disease, for example, and you need this percentage to stay between 0 and 100% after your raking process. So we developed a package to do the raking that includes all these different distance, and we can use any one of them depending on the particular needs that we have for the metrics we're looking at. Now we're going to look a little bit at how we solve this optimization problem. So we introduce a dual value that is called lambda, and we want to minimize over all possible rect values. So the distance between rect value and observation, and we introduce the dual value and the linear constraint here. So you can write this problem under the second dual formulation when you have to minimize over the dual and the convex conjugate. So one advantage of just reformulating the optimization problem is that we're going to decrease the size of the problem, because here the size of the problem is equal to the number of observation, where here the size of the problem will be equal to the number of margins, and usually you will have the number of margins smaller than the number of observations. So at the end, that means that your problem is smaller. You will end up with a smaller linear system to solve, which is always nice to have. So the problem, so we introduced the convex conjugate on our distance function, and we're going to solve this problem. So we're going to take the gradient with respect to the dual lambda, and we have a relationship between the gradient of the convex conjugate and the gradient of the distance function. And so in the end, we have to solve a nonlinear system, and we solve this system using a Newton's method. And when we have solved for the dual lambda, we can easily compute the rect values. So the formulation is a bit complicated, but in the end, that means that you have to solve iteratively several linear systems. And using this formulation, the linear systems are smaller than if you look only directly at the first formulation of the problem. So this is a detail of how you solve the problem with the Newton method. So you have to solve this system, and to solve this, you're going to take you're going to define this function phi, which is just a reformulation of this part. And at each time step, you're going to update your dual lambda by solving a linear system. And this one is just the derivative of this formula, this phi of lambda with respect to lambda. So basically, we just have to solve iteratively this linear system. We get the value of lambda, and from this, we can get the value of the raked values. So there is one additional thing that we have added to the problem is uncertainty quantification. So we suppose that instead of having, we suppose that we have our observations and our margins, and instead of being just a data point or a point estimate for this value, we suppose that we have a distribution for each observation in the table and each margin. So that means that if instead of being just an estimate that we are sure about, this is a multivariable, we have a distribution, multi-dimensional distribution for all these observations and margins. So we have the covariance matrix of the observations, the covariance matrix of the margins, and the covariance matrix between observations and margins. And what we want to get from this is to get the covariance matrix of the raked values. So the idea is to, we have some uncertainty on the initial observations and margins, and we want the corresponding uncertainty on the raked values. So for this, just to explain a little bit what we're doing, we go back to the initial problem, and this problem can be written under the form of this nonlinear problem. So we have first, when we take the gradient with respect to the beta of the initial problems that we are trying to solve, we get the first line here. And when we take the constraint, we have the second line here. And all this is equal to 0. And we can say that this problem has a solution that can be written under the form of a function phi of the observation and margins. And so the raked values are functions of the observation and margins. So this is just writing the solution of this problem. And what we say is that the covariance matrix of our raked values is equal to a matrix which is kind of the sort of the gradient of this function phi that determines the relationship between observations and margins and raked values with respect to the observation and the raked value. So we have the gradient, the transpose of the gradient here, the initial covariance matrix of observation and margins, and also the second time the variant here, the gradient here. So the idea is to explain more, this gradient is sort of when I move one observation or one margin, how much the corresponding raked values are going to move. So this is sort of explaining the sensitivity of your solution with respect to the observations and margins. And what we do now, we have to calculate what will be the value of this gradient here. And for this, we'll use the implicit function theorem. So we just derivate our first problem, and which will give us this formula. So this formula, we can just get the exact value here by taking the Hessian of our initial distance function. And this value here is just the matrix that we are looking at. So finally, we can compute this. We have the initial covariance here, and so we can compute the covariance matrix of the raked values. So now I'm going to give an example of applications. So I'm starting with a synthetic data set, so we can see more what we're looking at. So this is what the synthetic data set will look like. So for the synthetic data set, I just generate values for my table using some uniform distribution. Then I compute what would be the corresponding margins. So here I am sure that there is a solution to the problem because I've computed the margins so that there is a solution. I have a balance table. However, I do not want to do the raking on the table that is already well balanced because the problem would be too easy. So I'm just going to add some noise to the observations. So I have my initial observation, which are the balance table plus the noise. I'm going also to choose some covariance matrix. And so I suppose that now that my observation follow a multivariate normal distribution with the expectancy that I have chosen. So the balance table plus the noise and the covariance matrix that I have chosen. So now I can do the raking using the expectancy of the observations, and I can do the uncertainty quantification using the covariance sigma that I have chosen. So this is an example of what I can do. So here I plotted for the different value of the variable categorical variable x1. So we have 3 different categories for x1 and 5 different categories for x2. So I'm going to show the initial value with plus and minus their standard deviation. So the standard deviation come from the covariance matrix that I have chosen. And using the uncertainty quantification method, I can also compute the standard deviation on the rect values. So I also plotted in orange what would be the interval with the rect value plus or minus the corresponding standard deviations. So we can see that usually we reduce here the standard deviation on the rect values because here we do not have put uncertainty on the margins. I suppose that the margins are fixed and there is no randomness in the margins. The second thing that I have done is we can also look at the effect of one single observation on all the rect value. So here I look at the observation for when the variable x1 takes the value 3 and the variable x2 takes the value 4. And I look at the effect on the corresponding on all the rect values in the table. So I think that the rect value that is most influenced is the corresponding rect values for this observation. So also the one that goes with value 3 for x1 and value 4 for x2. And I can see that for the observation in the same column or the same row, we have a negative effect of the observation. That means if you increase the value of the observation here for here, that means the rect values for the other categories is going to decrease. So this suppose that the margins stay constant, and so if you want the sum to be equal to the margin, and you increase the value on observation of the observation, that means the other observation on the same row and column will need to be smaller so that the margins still match. So that the effect that we can see here with a negative effect for the other values in the column and the positive effect for the rect value corresponding to the observation. And you can see that if we are in a different row and column, we have a few influence of this observation. So we can also study the reverse problem, is to look at one rect value and see how much it is influenced by the different observations in the table. And you can see the same effect. So if we increase the value of the observation corresponding to the rect value will also increase because you will have to minimize the distance between the rect value and the observation. So if you increase the observation, the rect value increases too. to so that the distance between them stays smaller. However, if you increase the observation for in the same row or column, but different from the one you're looking at, you will need to decrease the reg value so that the sum stays the same. So that when you see the negative effect on the row and the columns here. And finally, what you can do, you can look at the effect of our uncertainty propagation method and compute as see how well doing the raking on the expectancy and the initial covariance works compared to have a sample. So I can generate samples from my observation because I have defined an expectancy for the observation with the covariance matrix. So for example, I can take one sample, rake the observation for this sample, and do this for many samples, and then compute the mean and the standard deviation of each rake value for each rake value, and I will have the mean, a sample mean for the rake values, and a covariance matrix for the rake values. So this I can do this for many samples, or what can I use directly the expectancy and the covariance matrix of the observation that I know here because this is a synthetic example. I rake the mean and I use the uncertainty propagation method to get the covariance matrix of the rake value. So the idea here is to compare the two methods and to see how much samples we will need to have the same, to have result as good as the uncertainty propagation method. So here I computed the reference as a result when doing 1 million samples. So I suppose that if I have 1 million samples, I get very close to the exact solution of the problem. And so, this is the reference. So this is the reg values computed when doing 1 million sample, raking each sample, and then computing the mean of the reg values. And this is the result that I get by raking just the known expectancy of the observations. And we can see that we obtain here the same results. In that case, I took 100 samples from the distribution of observations. I raked each of the sample, and then I computed the mean of the sample. So you can see here that with 100 sample, you don't have enough sample to compute well the mean without without a big error. And you can see that we still have errors compared to the reference values. And so here, to compute correctly the mean of the reg value, you would need at least 1,000 samples to get the same result as a reference, while you can do it directly by just raking the expectancy if it is known. So you can see the same result with 10,000 and 100,000, and it doesn't change. So the second thing that you can do is to compute the variance. So I use the uncertainty quantification method to compute the covariance matrix of the reg values, and so I have the variance for each reg value. And I compare the result with variance obtained when doing 1 million sample. So we can see that here we have a small bias, and we obtain a variance that is a bit smaller than the exact variance that we should have with this synthetic data set. However, when we compare to just having 100 sample from our distribution, the error that we have is much smaller. And even if we had 1,000 samples from the observation, it's better to use the uncertainty propagation method with the true expectancy and the true covariance matrix than just sampling using samples from the distribution and doing the raking on each of the sample. When we get to 10,000 samples, we actually start to get a better result doing the Monte Carlo simulation than with our uncertainty propagation method. However, when looking at the actual data set at IHME, we never have 10,000 samples. At most, we can have 1,000 samples, and usually we have just several hundred samples. So our uncertainty propagation method will work better on practical cases that we have. So this is to show that with 100,000 samples, we get a perfect result compared to the reference with the sampling method. So often people are also more interested in a confidence interval than in the standard deviation of the reg values. So also did the same thing for the lower bound of 95% confidence interval. So here to compute the confidence interval, I have to assume some distribution for the reg values. So here I use a multivariate normal for to generate the observation. So I also suppose that the reg value follow a multivariate normal distribution. And we can see that again, in 100 or 1,000 samples, we get better results with our uncertainty propagation method, such as doing a Monte Carlo simulation. And we need at least 10,000 samples to get good results. And we can see the same thing for the upper bound of the confidence interval. Here again, we would need at least 10,000 samples to get a good result for the confidence interval. So now I'm going to look at an application to a real data set that we have at IHME, and we're looking at mortality rates in the United States. So the problem is like this. So for each state in the United States, you have observation of the number of deaths by cause, by race, and by county. And you also have observation for all races by cause and by county. Observation for all causes by race and by county, and observation for all cause, all race, and by county. So these are all the observation we have, and the only margins we have is we know the number of deaths by cause of death for all races and all counties, so at the state level. So what we need to know is adjust all this observation, but we have an additional constraint here, is that we need to all this observation to match up consistently internally. That means if you look at the observation by cause, by race, and by county, we also want to make sure that if you add, we sum them over the cause, you get the observation for all cause of death by race and by county, and idem for this one. So not only we have to make sure that the observation add up to the margin here correctly, but they also have to add up internally. So we had to modify a workflow that the team using working on mortality rates was using. So they had a complicated workflow when they have to use the margins, which will be the number of deaths at the state level for different cause of death. And they did different raking process in 1D and 2D to get to the results and have all these observation adjusted correctly so that they match up correctly. So with our new raking package, the advantage you can take all the observations and all the known margins and do just one raking process, one raking step to get all the observation well adjusted to match correctly. So this is one advantage of the raking package that we developed. So now that we have done the raking, we can see that how changes in one observation will affect the reg value. So for example, here we're going to look at, so this is for Delaware, which has just 3 counties. So this is easier to see, to make plots with a small number of counties. So we're going to look at the observation for the Newcastle County, for deaths due to injuries, and for Black people. And we look at the effect of this observation on all the reg values. And so you can see that the values that will be the rate values that will be more influenced by this observation is the corresponding rate values. And you can see that you will have a small decrease of this is going to so you can see that if you look at all the causes of death, if you increase the observation for one cause of death, it's going to also increase the rate value for all cause of death. You're going to and another thing that however, if you look at the different race, for example, just increasing the observation from one race is going to increase the value for all races by decrease the value for the other races. So you can see also the effect of one observation on all the rate values. And reversely, we can see how change in the observation and the margins will affect one rate values. So here we're going to look at the rate value for the cause of death injuries. And so if you increase the margins for the injuries, it's going to change the corresponding rate value. And if you increase the observation for the total number of deaths, it's also going to increase the rate values corresponding to injuries. However, if you increase the number of deaths for the two other different causes of death, which are communicable and non-communicable disease, it's going to decrease the rate values for injuries. And here again, you can see that we're looking at the rate value for this for the rate value for Newcastle County injuries and Black people. And so the change in observation for this particular case is going to increase the rate value. However, change in observations for on the same column or row is going to decrease the corresponding rate values. And finally, what so we can see the effect on the different of the different observations and margins on our rate values. So the next application will involve inequality constraints. So in some cases, in addition to the linear constraints for the margins that I've shown until now, we can also want to have inequality constraints in our problem. So either you can just write inequality constraint like this with just a linear combination of the rate values that must be smaller than some threshold. Or you can write the inequality constraints with a penalty. That means in the case that there is no solution to the problem, that is, there is no combination of rate values that can respect both the equality constraints and the inequality constraint, what you're going to do is just to respect the equality constraints, but just try to minimize some penalty on the inequality constraints. So make C beta as close as possible to C, but it can be a little bit higher if necessary, if you want to respect the equality constraint. So for example, we can see can think of different applications. So here we're looking at mortality rates in two age groups. So 0 to 1 month old and 0 to 1 year old. So we actually, what we have is the number of deaths for each age group. From this, we compute the mortality rate. That will be the number of deaths compared to the population number for this age group. And from this, you can compute the probability of death, which is 1 minus exponential, the time interval, that's the population of the population. So that would be 1 month for the age group 1 month old, or 1 year for the age group 1 year old, multiplied by the mortality rate. And so the probability of death is the probability for all people that are all babies that are born to die before 1 month old, or to die before 1 year old. So the probability of death between 0 and 1 month is always lower than the probability of death between 0 and 1 year. So when we do the raking, we usually look at the two age group completely separately. So we take the table for the 0 to 1 month old, we do the raking and we obtain the rake values, and we do the raking for the 0 to 1 year old, we do the raking and we obtain the rake values. However, if you do that, sometimes it may happen that you end up with a probability of death that are smaller between 0 and 1 year than they are for 0 and 1 month. So you have to find a way to do the raking process so that even after the raking, you get a consistent probability of death. So we can just write the raking problem. So we have to minimize the difference between rake value and observation for the first age group and the second age group. We need to respect the linear constraint for the first age group and the second age group. And then we add an inequality that says that the probability of death for 0 to 1 month is smaller than for 0 to 1 year. So this is an example of the results that we have. So here I plotted the probability of death between 0 and 1 month and the probability of death for 0 and 1 year for males and females. So if we just use the equality constraints, and so here we're raking from each region to the national number of deaths. And if we do the raking just with the equality constraints without adding the inequality constraint, we can see that we have some data points in orange that will have a probability of death for between 0 and 1 month that is too high. Whether when you add the inequality constraint, you can see that the data points here in orange are shifted a little bit up, and so now you have some consistency between the probability of death between the two age groups. Another thing that you can do is to add weights to the raking. So usually our tables for the number of deaths are also given with some standard deviation on the number of deaths. So you have observation with small or big standard deviation because some observation may be more well-known than other observation. So in that case, we are going to add weights that are equal to the standard deviation of the observation. And so that means that observation with small standard deviation have bigger weights and observation with big standard deviation have smaller weights. So you can see that in blue, this is a raking without weights. So here are the initial observation and here are the raked values. And you can see that in orange, you have the raking with weights. So here you can see that the observation with a big weight that is small standard deviation are close to the first diagonal. So that means that the raked values are nearly equal to the initial observation. So if you have small standard deviation, you do not move the observation and the raked value is equal. However, when you have a big standard deviation and a small weight, the raked values can be very far away from the initial observation. And another possible application would be if you have data for each year. Yeah, this is the last slide. So if you have different data for different years and you see a trend in the observation, you want to keep the trends after the raking. And so this can also be translated into an inequality constraint. So yes, do you have any questions on this?
It's so fascinating every time to look at the statistics behind the results. We are at the time, so we have maybe time for one question or two questions if you have them for Ariane. Maybe one question I can ask. Like you showed the bias versus spread as a function of number of samples. What do you think is more important and where is like the cutoff in the number of samples?
Well, we do not really, well, in practice, we cannot really choose the number of samples because that's what we have. So this is more to show that with the current number of samples, we probably obtain better results with our method.
Okay.
Choosing the cutoff will be difficult because here this is a synthetic example, so we have to imagine for the real example with different number of categorical variables. It would be the cutoff may be different depending
I
on
see. It's
how many
depending-
observations you will
depending on the
have.
case.
So
Okay.
it's difficult to say exactly what would be the appropriate number of samples.
All right, if you have other questions, please come here and talk to Ariane. Otherwise, thank you for joining, and next time we'll be starting a mini series of talks with projects that came out of a program that we had at the eScience Institute about AI at GeoDub. So it'll be a series of 4 talks with AI methods applied in different contexts. Thank you so much, and we'll see you next time.